A very good morning to all of you. First of all, my sincere apologies for not being able to do this talk live. When you see this talk, I will actually be on a flight dealing with a family emergency. And I'm very grateful to the SOC for inviting me and allowing me to participate despite the circumstances. So today, what I'd love to share with you is results with Gemini from the growth collaboration. And I begin every talk I give with pictures of the most important contributors to the talk, which is my students and postdocs. And these students and postdocs are really the powerhouse behind the growth collaboration. And students and postdocs are part of the growth collaboration, and growth stands for the global relay of observatories watching transients happen. And the concept behind this National Science Foundation partnership in international research and education is that we begin discovery on one mountaintop, but very quickly we need to actually go around the globe for follow-up to try and understand and characterize fast evolving transients, very young supernovae, fast moving asteroids, all in a timely manner. So growth is an international collaboration, and it's as much a network of people as of telescopes. There are no new telescopes in this collaboration. It's all existing telescopes, existing infrastructure, and the people really bring it together. And here are the key players in growth. You see the various co-PIs from the different countries here. And the most amazing thing here is, thanks to jet lags and time zone differences, the team never sleeps. And that's not even a joke, because the team has so much energy that it has been a real pleasure to work with. The way we organize ourselves in growth, given the large number of scientists, not just peers, but also all the students and postdocs in the collaboration, the large number of telescopes, the large number of alerts, all this needs to be coordinated. And we do that dynamically through the Growth Follow-Up Marshal. In fact, this picture is now a bit outdated, because in collaboration with Josh Bloom at UC Berkeley, the next generation of the Growth Follow-Up Marshal, which is now the open source Fritz Marshal that any of you can download and use for your own purposes from GitHub, is now live and has been running for a while now. Over the 5 years that we were formally funded by the National Science Foundation between 2015 and 2020, we wrote 182 papers, and it was a lot of fun, well cited, and all that good stuff. So the discovery engines, the main discovery engines in the growth collaboration, are at Palomar Observatory. In the optical, it's this Zwicky Transient Facility. In the infrared, Palomar Gattini IR. And very soon, actually, we are going to be deploying the Winter Telescope at Palomar, which will be a new 1 meter, 1 square degree sensitive near-infrared imager at Palomar, which I'm very excited about. This will happen next month. And critical to the spectroscopic follow-up has been Gemini's rapid response capability. I don't need to preach to the choir here, but the queue scheduling facilities really enable Gemini North and Gemini South to respond within minutes. And this is unique to Gemini. And both North and South is just anywhere in the sky, anytime. It's a great hedge against weather. And GMOS, which has been the primary workhorse here, is an instrument that's available without any lunation constraints. Everywhere else, with Keck, with Palomar, with any large aperture telescopes, we struggle with the bright moon time when you just don't have an optical spectrograph mounted on the telescope. So initially with Gemini, we had some fun with the LLP program with a large number of rapid TOs. And since then, we've had many different programs led by many different PIs actually in the growth collaboration. Not just me, there's a program led by Anna Ho, one by Adam Miller, one by Robert Stein, one by Thomas Omuda, one by Leo Singer. And through this wide variety of smaller programs that we've been proposing for in various semesters, Gemini has continued to play a critical role in the scientific aspirations of the growth collaboration. So now I'm going to give you a taste of the collaboration science results. And I've broken this up into 4 sections, and I'll just spend a few minutes on each of these 4 sections to give you a flavor of the science. So let me begin with young supernovae. And the concept of supernovae evolve on luxuriously long time scales, right? We have days, weeks, in some cases months to study supernovae. But where growth really focuses energies from day one is hours after explosion. We really wanted to understand co-collapse supernovae in their infancy, within that first day after they were born. And Kawai Avishai Galyam led this effort from Weizmann Institute of Science. And what we were finding, what we were motivated by, were these very, very high ionization lines, like carbon-4, nitrogen-3, nitrogen-4, which disappear if you wait a day or 2 days, or depending on the amount of circumstellar material around the supernova. This flash in the pan that gives you these very high ionization lines just disappear. And so several students working with Avishai have actually written PhD theses trying to understand, when does a core collapse supernova show these flash ionization features? What does a population look like? When does it not show any flash ionization lines? When do you just see a featureless blue continuum? How quickly do these lines disappear? So on and so forth. And really try to understand the type of progenitor, connect the type of progenitor star to the type of core collapse. And I'd say, one of the biggest surprises, just which we published just this year in this, motivated by the science case, was a discovery of an infant type 1CN supernova. So again, I'm showing you 2 Gemini spectra, barely 2 days apart. And in one, you see this rich suite of lines, right? Neon 3, neon 4, carbon 4, carbon 5, oxygen 5, really, really spectacular spectrum on the top there. It's gone in 2 days. And the supernova, instead of almost all of the flash ionizers before this one, evolved to show hydrogen in the spectrum. And so they were in the type 2 category. This one, oddly enough, never showed any hydrogen. It had no hydrogen, and in fact, no helium either in the photospheric phase. So this was what we call a 1C supernova, because of the lack of hydrogen and helium. And Avishai in this paper presents a case for why this is a new class, a new window into our understanding of core collapse. And he dubs these as 1C N for the narrow line supernova spectral features that we see. Another example that again caught us completely by surprise was an infant ultra-stripped supernova, where we see the flash ionized helium-2 4686 line that you see over here, and we see it disappear in about 33 hours. The spectrum, 33 hours after explosion, you don't see that line anymore. And this thing, if you look after the shock cooling dip, you actually look at the second part, the second peak in the spectrum, and you fit that and you try to compute how much ejecta there is, it's really tiny. So it's not just a stripped envelope supernova, but an ultra stripped supernova. And it is so extremely stripped that if you work through the numbers, the only way to strip such a supernova is through a compact companion. So this is what Thomas Torres and others have theoretically postulated as a class of ultra stripped supernovae, which are sort of the penultimate step towards forming a compact neutron star binary. So you already have something that is stealing all the material. It could be a white dwarf, a neutron star, or black hole, and you just formed another neutron star at the end of this explosion. So this binary, if it remains intact, could actually be compact enough to then merge in less than a Hubble time. So seeing some direct evidence of a system like this being born in action in real time was a really fun result that a growth student, Kishore Loide, wrote, and encourage you to read his paper. Now I'd like to move on, in the interest of time, to section 2, which is on relativistic explosions. And here I'd like you to speed up time scales, right? I mean, supernovae, as I said, tens of days, they live on the if you plot peak luminosity versus characteristic time scale, then a decade ago, we were getting very excited about novae, supernovae, finding transients in the gap between novae and supernovae. In the past decade, this diagram has gotten squished, and we've been pushing to sub-day timescales. So what sort of optical transients actually evolve and explode on sub-day timescales? And the well-known piece of the relativistic explosions categories is, of course, gamma ray bursts. There's decades of gamma ray burst science with Gemini. There's no way I'm doing justice to any of that in this short talk. And what's new is that initially Gemini would go and observe gamma ray bursts that were discovered by, say, the Swift satellite, that was well localized. Now it's also been trying to find the afterglows of gamma ray bursts that are coarsely localized by the Fermi satellite, or not even that, but gamma ray bursts that are discovered first in the optical. So here are a couple of examples of things that look exactly like a gamma ray burst afterglow, but they're not triggered by a gamma ray satellite. They're discovered in the optical. And in some cases, we just missed the gamma ray emission because the satellite was looking in the wrong place. In the other cases, it could be an untriggered GRP afterglow. And we have dozens of examples of this now. We're finding more and more, as we understand the gamma ray burst population more, we are finding more and more exceptions to the rule of the sort of two categories, right? Where broadly speaking, you have the short duration gamma ray bursts that come from neutron star mergers, and the long duration gamma ray bursts that come from collapsars, which are deaths of massive stars. In this paper, graduate student at University of Maryland working with Leo Singer, Thomas Amuda, and the growth collaboration discovered an extremely short duration collapsar. So the shortest duration collapsar. So if you just look at the duration, it should be a short GRP, and that's what he was actually looking to find the afterglow of. But if you look at some Gemini photometry in this case, you see this inset here. The light curve deviates from an afterglow model and shows a bump that is consistent with coming from a supernova, from a collapsar in this case. So this is the shortest duration collapsar that we have discovered to date, and encourage you to read Thomas's paper for more details. So that said, I'd now like to switch gears again for the third time to fast blue optical transients. And at this point, you might realize that I've another topic to cover. And a Caltech graduate student, Anna Ho, actually comes to the rescue here. She's a Caltech graduate student until a couple of years ago, and she's now Miller Fellow at UC Berkeley. And she's also going to be giving a talk at this meeting. So I was going to tell you about her discoveries of the koala and the camel and all the fun with fast blue optical transients, but I'll leave all of that to Anna's talk and skip right ahead to section 4. And section 4 is on multi-messenger astrophysics. This is the science topic that is actually sizzling with excitement in this decade. There have been massive breakthroughs in understanding cosmic explosions through multiple messengers. So not just photons and light, but also gravitational waves or also high energy neutrinos. And on the right, I show you a picture of the IceCube high energy neutrino detector on the South Pole. And it's spectacular because just in the last few years, there have been at least 4 events, 1 blazar and 3 tidal destruction flares, where coincident with the high energy neutrino, we see an electromagnetic counterpart. And 3 times at least was a tidal disruption flare, not even an extremely relativistic or jetted tidal disruption flare, pretty normal looking TDE with a strong dust echo. This Gemini has also been helping with follow-up of these high energy neutrino candidates and helping vet them and understand which ones could be associated, which ones not. And now I'd like to focus on the picture on the left here, which is gravitational wave counterparts and the fun science we've been doing in following up gravitational wave triggers from the LIGO, Virgo, and now soon Tagra is joining this gravitational wave interferometer network. So as far as neutron star mergers go and neutron star black hole mergers go, the key motivation to study these cosmic explosions with multiple messengers is to understand the origins of heavy elements. So everything you see in blue here is synthesized by supernovae of different flavors. Everything you see in yellow here is synthesized by our process nucleosynthesis, which is the rapid capture of free neutrons to make heavier and heavier nuclei. And the best site we have, and the only site with completely direct evidence, arguably, of our process nucleosynthesis is in fact merging neutron stars. And when we encounter the situation of the synthesis of very, very heavy elements, then inherently you're filling out SPDF shells, and inherently you have millions of line transitions, and unavoidably you have very, very high bound opacity. We're talking about 10 centimeters square per gram. And the only way to overcome this bound opacity is sort of to look at the emergent spectrum, shift from the optical in the infrared, and improve our infrared tools. And the very first time, this majestic event from August 17th, 2017, which was the first binary neutron star merger that was directly detected in gravitational waves, when that trigger was announced at 4 a.m. on this day, the most amazing thing about this was that this lit up the entire electromagnetic spectrum. And let me just remind those of you who may not be fully caught up with the story, is that as soon as the Earth rotated and the sun set in Chile, there were 8 telescopes that were observing the afterglow from this event, the electromagnetic counterpart to GW 170817. And Gemini, with the Flamingos 2 camera, took this beautiful picture that you see here in the JHK bands. This was a picture taken by Growth Kawai Leo Singer. And since that first night of confirmation and discovery of that pinpointed location of the electromagnetic counterpart in the galaxy NGC 4993, Gemini got a sequence of infrared spectra and photometry, also with the Flamingos 2 camera, till it was almost impossible to observe because the target just got too close to the sun and faded very quickly. But you could see these beautiful spectra with spectacularly broad lines, which shockingly matched predictions from many years ago, theoretical predictions from many years ago, by just overplotting some models from the grid onto the data, not even trying to fit it, just overplotting, which is so you can compare data in gray and smoothed in black to the red line here. And this was by far the most sort of vivid evidence. Infrared spectroscopy was the most vivid evidence that we have of the synthesis of our process elements in a binary neutron star merger. There is just no way any supernova, any transient of any other sort could produce the lines that we see here. And these are not single individual lines, but all blended together, many, many different lines with very, very high velocities as well. And then since then, we have made a lot of progress and tried to discover even more the electromagnetic counterparts to gravitational waves. There was an entire observing run, the third gravitational wave observing run, where there were many triggers for binary neutron star mergers and neutron star black hole mergers, a total of 13 triggers. But the median distances were really high, and the median localizations was over 4,480 square degrees. Our tools were sharper. We had this Wiki transient facility with the 47 square degree field of view, and you can see how quickly we could map these ginormous areas within a few hours after merger, and less than 4 hours after merger. But the challenge was all in the follow-up, right? Inside those 13 gravitational wave event localizations, there were 2.1 million candidates. And it took multi-step machine learning, all kinds of photometric and spectroscopic follow-up of all of these candidates to bring down that funnel to conclude that with all the follow-up data in hand, without which we would be able to say nothing, with all the follow-up data in hand, none of those triggers or none of the data associated with those 13 gravitational wave triggers in the third run were consistent with physically being associated with those neutron star mergers. So there was 0 kilonovae after all of this. Gemini played a key role in this follow-up game here. And so what we were able to conclude was that perhaps GW170817 was not the norm. Perhaps the luminosity function is skewed towards a significant fraction of kilonovae or electromagnetic counterparts to neutron star mergers being fainter than GW170817. So there's some constraints you can derive even from the non-detections in the third run to learn about what the underlying luminosity function would be. Furthermore, you can constrain the rate. I mean, it's been 5 years since the discovery of GW170817, and so you can ask the question if there were more, how common these events are, by looking for these events completely serendipitously. It has nothing to do with actually the gravitational wave rates. I mean, you can see the gravitational wave constraints in light blue here, but independent of that, you can now use just the wide field optical surveys, many different ones, to try and constrain the rates of these events. And the rate has to be less than something like 900 per gigaparsec cube per year if GW170817 was a fair example of the luminosity function of such events. And this pipeline that we are using to search for kilonovae serendipitously is called ZTF REST, just for fun, for real-time searching and triggering. It's a pun on the word rest, right? Because it's really not really resting, but searching all day, all night, every night, even when the interferometer is offline. And the idea is that we look at the fastest fading events, and we try and understand them in real time by getting prompt follow-up and seeing if any of them are consistent with kilonova. And we found many a gem in this data, many gems of different types even, but none of them are actually consistent with the kilonova. So they strongly constrain the rate of kilonovae by doing this serendipitous search. In just the last couple of minutes here, I'd like to conclude with some thoughts looking ahead. And I'd say in the coming few years, let's just say the coming 5 years, one of the things I'm most excited about is neutron star black hole mergers and finding the electromagnetic counterpart to a neutron star black hole mergers. We know they are no figment of a theorist's imagination. In the third observing run of LIGO Virgo, they found these events. They found a couple of these events with some with pretty extreme mass ratios. So where the neutron star is probably swallowed whole by the black hole. Some with more tantalizing mass ratios where maybe there was possibly some ejector, right? The localizations were much too coarse. So in the coming observing run, the fourth gravitational wave observing run that should start in March 2023, I think we have a real shot at understanding and discovering the electromagnetic counterpart to neutron star black hole mergers. And of course, at the very end of this fourth gravitational wave observing run, we'll have a new giant in optical time domain astronomy in the room, which is the Rupin Observatory. And this will be so incredibly powerful that it will do tremendous amounts of science, not just in the multi-messenger arena, but in all types of time domain astronomy, in all aspects of astronomy, in fact. And I'm hoping that many of the students and postdocs trained by the Growth Collaboration in the last few years will be leaders in the Rupin time domain science world. And Gemini has been thinking ahead and is building this amazing new spectrograph called Scorpio. And I'm sure it's going to do fantastic follow-up. And we'll have a real treat of spectra and science that will be enabled by this instrument. And with that, I'd like to thank you again for your time and patience with this recorded talk. And I'd be very happy to answer questions as soon as I'm able to get internet again when the flight lands. Please put your questions in Slack and I'll be sure to answer them. Thank you so much and hope you enjoyed the Gemini Science meeting.